Greetings and welcome to a new video about analog filter design. In this example we will discuss the inverse Chebyshev response for our high-pass filter circuit. We will see how we can calculate the components for our state variable circuit in this example. Of course we will see everything step by step and verify these in SPICE simulations. Okay, our design objective is shown here. We'd like to design an inverse Chebyshev response active high-pass filter, and we will use a state variable circuit. And our high frequency gain should be 1, so it means 0 dB. The specifications for our filter design are shown here. Maximum passband ripple must be 1.5 dB. The minimum stop and attenuation, a minimum is 20 dB. The passband frequency is 2 kHz and we have a stop band frequency of 1 kHz. Now briefly about these specifications, of course we have seen this before in the Bode response, Chebyshev and the Bessel response designs. So let's go briefly through these specifications. The stop band frequency, at this frequency of 1 kHz, we need to have a gain which is minus 20 dB, or the attenuation must be 20 dB. That's actually the meaning of these two specifications. And the maximum passband ripple, meaning that we have a maximum of 1.5 dB decrease at this frequency. It can be lower, so it can be, for example, 1 dB or 0.8 dB. That is also allowed. But this is what is maximum in this case allowed. Okay, let's go to the solutions. First, the filter order. In this case, we relate again our A max and A minimum to the epsilon P using this formula. We have seen this before, and that will result in this value, and epsilon S to this A minimum, and you get this value here. Now, taking these two values together, we can calculate the filter order we need for our design. And you will use now this formula. You see again the epsilon S and epsilon P, which is determined, and FP and FS from our specifications. Now substitute the values in here. You get here 2.6063, which should be of course an integer value for our realization, so we go for NF3. Okay, next step, we need to go to the normalized Chebyshev poles, the natural frequency and the quality factor per stage. The poles for the normalized Chebyshev response are given by this expression. You see here the real part and the imaginary part. There are also some parameters. Let's go one by one. The K here is our pole number. The N is our filter order, so we have N3. And the A here is some value which is calculated using this formula. So we have now here our A also. Now we can go one by one and looking at the poles. So we have now a third order filter. We already know that. That requires one real pole and one complex conjugate pole pairs. That is actually what we'll see here. And that means actually we get 3 poles in total. Now the pole pair is then K for 1 and for K is 3. So if you substitute here K is 1, you get the real value here. If you substitute K is 3, you also get this real value. But the imaginary value will change if you go for K is 1 and K is 3. But they are of course connected to each other, so they make a complex conjugate pole pair. For K is 2, if you substitute here the K is 2, you get actually this value, and the imaginary value will be then 0. So you see here the 3 poles, and we will need to use this for our design. The poles we have now calculated are located on an ellipse. That is for the Chebyshev response the case. And as said before, we have 2 stages for our design. The natural frequency is given by this expression, and here you see here the sigma, which is the real part, and omega, which is the imaginary part for our poles from here. And the quality factor is given by this expression. Now you also see here the subscript T, and that T is the stage number. And again, the small letter sigma is our real part of our pole, and the omega is our imaginary part of our pole. So we go one by one, looking at the stage 1, which is our complex conjugate poles, P1, 3. So these are the poles. And now you can calculate the natural frequency, and this N is not the filter order, it's just referring to the natural frequency. And now the T is 1 because we look at the stage 1. You look at sigma 1 and the omega 1. Now sigma 1 is that one, that's 1, and then we have also the omega 1. Now you substitute the values, you get this omega N1. And the quality factor, again using this formula, you get here the 1.2435. Stage 2 is the real pole. You get this. Now looking at this one, you actually only have the real part and not the imaginary part. I will just show you in full picture what it does if you just substitute also the real and the imaginary part in it. So you get only this 1.1717. and the quality factor is here always 0.5 for a real pole. So that is actually the calculation for our stage 1 and stage 2 for our natural frequency and the quality factors. Okay, now bringing all that together, we need to go now in the step 3 to the normalize inverse Chebyshev, because we now did a lot of calculation for the Chebyshev poles and the frequencies and the quality factors. Now we need to convert that to the inverse Chebyshev. Now the quality factor of the inverse Chebyshev will stay the same as the quality factor for the Chebyshev. That means the quality factor for the inverse Chebyshev, denoted by this to the power minus 1, is equal to the quality factor of the Chebyshev response. But the natural frequency of the inverse Chebyshev response is the 1 over that natural frequency of the Chebyshev response, so it's given by this expression. Again, we will use the notation to the power minus 1 to refer to the inverse Chebyshev parameters. And the t is again here the stage number. Now for each stage we can go again through the calculations, and now we will denote the poles for our inverse Chebyshev again by this superscript to the power minus 1. Now we calculate here the natural frequency, again using the natural frequency from this calculation for step 2 for our normalized Chebyshev poles. So 1 over that value, 1.4570, you get this natural frequency. And the quality factor is exact same as before for stage 1. And for stage 2, you get this, and you do 1 over that value, you get now this 0.8534. The quality factor is again 0.5, that stays the same. Now we need to go to the normalized inverse Chebyshev response zeros also per stage, because we will have zeros in our design. That is the characteristic of an inverse Chebyshev, like the elliptic filter response. Okay, the zeros are given by this expression. You see again here the t, which is referring to the stage number, and the omega z, meaning the zero frequency. And now we see here the formula, and there you see again the filter order, which is n3, and again the t for the stage number. So we go here, and that means we have now 2 times 3, which is 6. And now we can calculate the 0 for the first stage. That is then given by this expression, like 2 times 1 minus 1 will be then of course 1. So we get here cosine of pi over 6 in the denominator, and that will result in the value of 1.1547. Okay, now for stage 2 we also have the 0 that can be calculated by substituting in here 2. So you get 4 minus 1 in total to the minus, times pi over 6. That will then result in 1 over the cosine of pi over 2. But the cosine of pi over 2 is 0. That means this 0 will be then, the zero frequency actually will be then at infinite. So we will have 2 zero frequencies, one at 1.1547, the other one will be at infinite in this case. Okay, now let's go to the summary and what we have so far calculated. This is a summary of the results. I will refer here to the low pass filter stages. Why? Because we do the calculations so far for the low pass prototype filter. We will shortly convert that to the high pass filter, and we will see how we need to do that. So again, the stage 1 and stage 2, the quality factors, the natural frequencies, and our zero frequencies are shown here. So we need to now denormalize or scale it up to the actual component values. So we need to go to the inverse Chebyshev natural frequency and the zero frequency per stage. Our frequency scale factor is given by this formula, which is Kf is equal to 2 pi fs, or just omega s. And fs is our stop band frequency, so that means 2 pi times 1000 or 2000 pi radians per second. There's an important note here to clarify what we actually do here. We do the frequency scaling using the stop band frequency and not using the passband frequency. We use the passband frequency scaling in the Bode response, Bessel response, and the Chebyshev response. And for the inverse Chebyshev response and also for the elliptic response, we should use the scaling using the stop band frequency. That means the following. Now, since we scale the frequency scaling, do that with the stop band frequency, at the stop band frequency of 1 kHz in this case, you will have your stop band attenuation exactly as 20 dB. That is what you will have. But your passband ripple, so at this 2 kHz, it will be not 1.5 dB, it will be lower. Of course, perfect, because this is maximum allowed for our design. So this is an important note for this specific response, which is an inverse Chebyshev response. Now going to the stage 1, and now we get a very important transformation. We do now the state variable high pass filter circuit, of course, and now we need to do the natural frequency of this high pass filter circuit will be Kf divided by the normalized values what we see here in this table, because these values are for the low pass filters. So we need to go and using the Kf over the values here. Normally we did that Kf times the values here, so that is actually the change what we actually make here. And now you get actually this 9155 radians per second for the natural frequency for the first stage, and zero frequency in the similar form. Again, looking at this value, you get here 5441 radians per second. Again, we normalize the components in our low pass prototype filters, but they are given here with a hat on top of it just to recognize them as normalized values. And we have now our scaled up or denormalized natural frequency and the zero frequency. Now going to the stage 2 in a similar form, passive RC high pass filter circuit. Again, we see the similar operation in order to go from the low pass to the high pass filter circuit. And now we see here the value again, 2000 pi again divided by this natural frequency. That is of course also in zero frequency because that is what the frequency was. Now, if you do the calculation there, you will of course get nothing, so that is actually not included in this example. Okay, now we convert these normalized values in the low pass prototype form to the denormalized values in our high pass circuit. And now you see the high pass filter stage 1 and 2. The quality factor stays the same, but you have now here the natural frequency from here, and the zero frequency from here, and natural frequency for the second stage from here. Now, we will need to use these values in order to calculate the components in our filter circuit. So, step 6 is going to the circuit realization and then the component values, and we see here again the required information for that design. Now, for that design, we need to use this circuit. This is a state variable filter circuit, which is specific for the high pass filter. You see the part here up to this node is actually the high pass filter state variable second order. But this addition of C7 and R7 makes actually a third order. So this is the passive RC high pass filter, which makes this a real pole. We start the calculation by first selecting the values for the resistor and the capacitors shown here. So the resistor R, 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 R. So we have 4 R's. We take it as 100 kilo, and these two capacitors we select as 100 nanofarads. And then we can calculate now the rest of the component values. We start with stage 1, which is our state variable high pass filter circuit. And there we have the R1. We will set that equal to R4, that's actually shown here. And that can be calculated using this. We see the quality factor of the first stage, that's actually from the table. We see here the natural frequency, also from the table, and then also the selected C, and that will result in 1358 ohm. Now R2 and R3, that's next, and that's also equal to each other, and that's then given by this expression. You see again the natural frequency and the selected capacitor value here, and it will result in 1092 ohm. R5, which is then this resistor, will be calculated using this formula. You see the resistor we have selected, the quality factor from the first stage, the zero frequency from the first stage, that is shown here, and the natural frequency from this first stage, that's shown here. Now, if you substitute here the values and calculate that, you get here 124.3 kilo ohm. Okay, that is now for the stage 1, and we also know that we need a high frequency gain of 1. So that means we need to set the K is 1 for the formula in order to go for this R6. So the R6 will be then K times this R will be then just 1 times the resistor we have selected. So that's also 100 kilo ohm. Stage 2, that is the passive, this part, RC high pass filter circuit. That is given by this expression. You see the natural frequency is equal to 1 over the R7 and C7. Now in here we have two unknowns, and we only know this, so we can select, for example, the capacitor as 100 nanofarads, and then we can calculate the R7. So C7 is also 100 nanofarads, so R7 will be then 1 over the natural frequency and the capacitor we just selected, and that will result in 1358 8 ohm. This is exact same as the R1 and R2. That's because we have also selected the same capacitor here. That is the reason. Okay. We have now everything, so the design is in fact completed. Let's also calculate the cutoff frequency for our design. That is calculated using this formula for the high pass filter. You see here the stop band frequency, the cosine h, which is the hyperbolic function. You see the inverse of that one, the epsilon s, which is the scaled value from the A minimum, and our filter order. Now when you substitute here the values, here you get here 1000 times the coefficients here, you get here almost 1.54 kilohertz. Okay. Now let's go to the simulation result. These are the values we have selected and what we have calculated also here. You see that, and everything is here in summary given. And this is a circuit in the SPICE simulator. So you see here the input voltage, you see here the output voltage, you see the complete circuit with all the resistors and the capacitors we have selected and calculated. And we have also 4 operation amplifiers. Now let's go also to the simulation results. This is the Bode plot. You see here the gain in the vertical axis and the frequency in the log scale here. You see indeed that the high frequency gain is 0 dB, so that is or 1, that's indeed correct. We see the gain is minus 0.59 dB at 2 kilohertz. So that is actually the requirement from here. So the FP, which is 2 kilohertz, that's the passband frequency, there we should have a maximum gain reduction of 1.5 dB. We only have almost minus 0.6 dB. But how do we calculate that? Now that can be done using this formula. You see here again the filter order, passband frequency, stop band frequency, and our epsilon s, and and also the 10 log of that complete expression here. Now when you do the calculation here, you get here using the values from what we have calculated, 0.59, which is very close to what we have calculated here. So that's indeed correct. Okay, the next one is about the cutoff frequency. This is the gain of minus 3.01 dB, and that happens at 1539 hertz. And we have also calculated that exact same frequency. That is indeed correct. The next important part is the gain, which is minus 20 dB at 1 kilohertz. Now that is an important parameter we need to also check, because at that stop band frequency our required minimum attenuation must be 20 dB. So that is indeed correct. And again, we see that at that frequency the attenuation we get is exactly as we have here. But we have here less ripple or less reduction in the gain because we do the frequency scaling according to the stop band frequency. What we also see is that this is going down rapidly and it is increasing. And it comes again to a point which is not above the minus 20 dB. That is interesting, because if I go above, that will mean that I can get a higher gain at a frequency which is smaller. And this happens in this case at 500 hertz. What we also see is the valley, which is this sharp decrease, which happens at approximately 866 hertz. Is that a frequency we have calculated? Yes, we have calculated the zero frequency, which was omega z1, which was for our first stage, and that was 5441 radians per second. And if you convert that to the hertz, so just to divide this by 2 pi, you get this value very close to this value. So it is indeed correct. So we have verified our stop band attenuation characteristic specification, also the passband frequency, and also our high frequency gain. So the design is in fact completed. Alright, it was our example considering the inverse Chebyshev response for the active high pass filter. We have used our state variable circuit in order to calculate the components, and we have verified our findings using the SPICE simulations. If you have any questions, comments, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.